Hi, I'm now Koshimoto from Osaka University. I'm very glad to see you all here in Osaka, and I hope you enjoy your stay in Osaka and Japan. Okay, let's get started. So I talk about the detection efficiency of the MOA-II 9-year survey for free floating planet events. And so conventionally to correct the observed distribution with a model prediction, we need a detection efficiency, and conventionally 1D detection efficiency as a function of TE was used. And in this talk or in this work, we showed that 2D detection efficiency as a function of TE and theta is actually needed. Okay, I think I can almost skip this, right? That's microlensing. The important thing is observable of the microlensing is the event time scale, PE, and this is defined as angular Einstein radius, theta e divided by the relative proportion, mu, and this is proportional to the square root of the lens mass. So by observing many microlensing events with different time scales, you can do the census of various populations in our galaxy, from free floating planets to black holes, so including the planetary systems. I think so. These populations are very interesting, but of course I focus on the free floating planets. Okay, so to measure the occurrence rate of a population, here is a procedure to the step-by-step procedure. First, we need to observe to find microlensing events, and then we need to select microlensing events to make a statistical sample, and then we need to correct the distribution using the detection efficiency to compare with the model. And finally, you can model it to measure the occurrence rate. And in this work, as Taka overviewed, these four steps are corresponding to this written in blue. So we use MOA-II 9-year survey data, and we selected the 35 microlensing events from that, including 12 short time scale events with t less than or shorter than 1 day. And as I said, we introduced 2D detection efficiency for the first time. So in my talk, I focus on these bold two things. Okay, so let me introduce the finite source effect. This is already explained by Chemek and Taka, but when the length mass is low, like FFP, the size of Einstein ring theta e becomes comparable to the size of the source star, theta star. So on the top shows the case where we don't consider the finite source effect. In this case, the source size is much smaller than the Einstein ring, and you can see this type of sharp shape of the light curve. On the other hand, if you consider the finite source effect, or when the angular Einstein radius is comparable or to the source size, you can see the finite source effect, which causes this peak rounded in the light curve shape. And the good thing with the finite source effect is with the finite source effect, you can measure the angular Einstein radius theta or equivalently mu when you combine the information from the TE. And the tighter constraint on the length mass can be obtained. So here are some example of short time scale events. I think Taka already showed these right curves, but I picked 4 events. So on the top left, the finite source effect were not detected since we don't have the peak coverage. And on the top right, we measure the finite source effect and measure the angular Einstein radius, since this peak is well covered. And on the bottom left, the entire right curve is well covered, but this right curve model is still consistent with point source. And on the bottom right, the entire right curve is well covered, and we detected the finite source effect and measured the angular Einstein radius. And we did the partial analysis for these two events with the finite source effect detected. And the first one is this event. This is also already introduced by Taka, but we conducted the Bayesian analysis using a model of our galaxy as a prior to get this posterior distribution of lens mass. And this reveals that the lens mass is likely to be around the Neptune mass. So this is the fifth Neptune mass FFP candidate to date. And this one has the shortest time scale in our sample, and the second shortest time scale in all events discovered to date. And by the Bayesian analysis using the galactic model, this is the posterior distribution of the lens mass we get. And the two different colors correspond to different prior on the mass function, but both are consistent with the terrestrial mass. And this is the second terrestrial mass FFP candidate to date. Okay, and this is the posterior distributions of TE and theta E calculated using the MCMC for 12 short time scale events with T shorter than 1 day with a uniform prior in log TE and log theta E. And these two panels with blue text FSF detected the events I introduced earlier. And for the other 10 events without the finite source effect, still have lower limits on the angular Einstein radius theta E. And if we apply the galactic prior, from the structure of our galaxy, we can guess the distribution of the relative proper motion, and then so considering our galactic structure, then the mu error is likely to be between about 0.8 to about 20 mass per year, and this gray dashed line shows that region. And by applying this prior, some events, the theta E values are effectively constrained even without the finite source effect. So this is one of take-home message in my talk for short time scale events such as FFP events. Events without finite source effect can be nearly as useful as those with the finite source effect when applying a galactic prior. Okay, so let's move on to the detection efficiency part. So as I said, conventionally the 1D detection efficiency as a function of TE was assumed since for this light curve shows the case where TE is long enough for non-FFP events. In this case, the finite source effect affects only the peak part of the light curve. So the event detectability itself is rarely affected by the theta E value. So this is why previous studies assumed 1D detection efficiency as a function of only TE. However, this is taken from Shemek's slide, but when TE is very short, like the FFP events, the entire event time scale itself is affected by the finite source effects. This means the event detectability or the detection efficiency is affected by the theta E value. So this is why we need to consider the 2D detection efficiency as a function of TE and theta E. Okay, so to compute the detection efficiency, we conducted the image level simulation of artificial events with a finite source effect. So this is a real difference image, and we inject artificial event with a given parameter, and then conduct the photometry using the same pipeline as we use for real data, and then get the right curve of artificial event. Then we check if this event meets the actual selection criteria that we use for actual data, and then consider if this is detected or undetected. And by repeating this injection and recovery tests of 64 million artificial events, we computed this 2D detection efficiency as a function of the timescale TE and theta E. And the computed area is corresponding to this region of the relative proportion values. And from this column map, you can see even at the same TE value, you can see the detection efficiency dependence on theta E when TE is about less than 1 day due to the finite source effect. And when you try to calculate the 1D detection efficiency using this, you need to assume the weight of each grid or each value of TE and theta E, which corresponds to the event rate at the TE and theta E value. And because the event rate is dependent on the mass function or free floating planet mass function, which is what we want to have. So basically, the 1D detection efficiency, depends on the mass function you assumed. So this is a take-home message number 2. So the conventional 1D detection efficiency as a function of TE is inappropriate for the FFP analysis. So we have to use the 2D detection efficiency because first, the detection efficiency for free floating planets depends on theta E due to the finite source effect. And second, even when you try to integrate it over theta E to get the 1D detection efficiency, but it requires an assumption on the FFP mass function, which is what we want to measure. Okay, so this is a summary of my slides. So I have 2 take-home messages. Number 1 is for the FFP events without the finite source effects can be nearly as useful as those with the finite source effect if you apply the galactic prior. And number 2 is 2D detection efficiency is needed for FFP analysis. So yeah, that's all. Thank you.
I have a question. So in principle, the efficiency also depends on
Limb darkening.
which
Yes.
it's the constant filter, so it doesn't change a lot, but it does change depending on the spectral type of this card.
Yeah.
So did you check? I assume this is negligible, but did you check?
Did we check? I don't remember. Yeah. But the point is, if the for example, the mass function depends on the limb darkening one, and the limb darkening is a source parameter. So I think if there is a dependence on the limb darkening, it doesn't affect the final mass function, or how to say that. It doesn't violate the theory.
Well, in principle, for each source, you should have a different efficiency.
Yes, and we didn't. Yeah, so the answer to the question is we haven't checked it. Sorry.
Well,
So just going back to your really short duration event.
Mhm.
So you showed the Bayesian posteriors on the
Yeah.
on the physical parameters there.
Mhm.
But one of the things you brought up is that your posterior depends on what you adopt as your FFT mass function,
Mhm.
right? And so given that this is the shortest event, it's sort of an extrapolation beyond where you have other data where you're fitting your mass function. So I was wondering how that all sort of reconciles, right? If your goal is to use this to predict the FFT mass function, and this is going to be your lowest data point, then how are you sure that your mass function extends to those low masses in order to build out that posterior?
So I'm not sure if I understand your question well, but yeah, so since we are not sure that the mass function extends to, the, how to say, the lowest mass, the sensitivity on the, how to say, the lowest mass in that our sample has. This is why we use these two different priors, and the orange one is actually has a break of the 10 to the minus 6 solar mass, which is about the minimum mass that we think our sample has a sensitivity. So, and after the break, it has a, how to say, flat shaping of mass. And so, yeah. And the blue one is just extends the same power with minus one.
So the takeaway is that using two pretty different priors, you end up with pretty similar masses.
Yes, at least we have the upper limit on around here. So yeah.
Okay, cool. Thank you.
But I mean, in principle, doing this right means that you have to adopt a prior, do your analysis, and make sure that your posterior is consistent with your prior, update your prior, and then repeat. You can do that with some higher or Bayesian analysis. There's one more question.